Okay, it looks like we might not have any chair here, so maybe let's start with the talk. My name is Mateusz Baran. You may call me Matthias if you prefer. I will talk today about JuliaManifolds and our approach to computing and showcase what our ecosystem is currently capable of and what you may expect in the future and why you might care about manifolds at all. Okay, so I will start with a less abstract way of talking about manifolds. If you have ever encountered this concept, it's mostly quite abstract, very difficult math books. I will try to demystify them a little bit here and provide a more straightforward approach. I will highlight two parts of the ecosystem that I think are fairly mature and useful. The first one is Manifolds, developed by Ronnie, who is sitting here with us, and it's a package for optimization on manifolds. And the next part, the next large part of the ecosystem that I think is interesting is statistics on manifolds. Last slide will be the future of the ecosystem. So let's start with why we might care about manifolds at all. First of all, it provides very generic support for complicated data structures that may contain vectors, matrices, structured data, neural networks, whatever you want. And the key part here is that you can develop algorithms in a way that doesn't require flattening those structures into vectors or arrays. You can keep the complicated structure and work on this. You can develop complicated algorithms. Basically, any Manifold optimization algorithm works with any complicated data structure. The second reason to care about manifolds is that they enable a very nice way of handling constraints. If you have some constraints on your data or your model, you may be aware that, for example, you cannot use straightforward Euclidean optimization methods, but you need to introduce constraints which limit what kind of solvers are available. They introduce some penalties to performance. In this approach, if you have a certain kind of constraint, we support, for example, orthogonality constraints, spheres, and lots of other types of constraints. It's not arbitrary. It's not like you can take any constraint and fit it here efficiently, at least. But if your constraint is one of the few that can be easily supported in this way, then you are in luck. You still have access to all the standard tools that are available for unconstrained problems. So we get away with constraints and just replace them with expressing algorithms with special operations. We further reduce numerical issues caused by local parameterization. So you may be aware that another way of, for example, dealing with constraints is you just introduce the parameterization. For example, on a sphere, you may introduce a map that transforms this constraint, for example, optimization problem or optimization or another data analysis on a sphere into analysis on a flat space. without any constraints. But this often leads to issues. For example, if we have a sphere, then it's not possible to map it into an Euclidean space without removing at least one point from the sphere, right? So if you have data that is all around the sphere, you may have severe numerical issues when you reach the limit of your map. The way we solve the problem of constraints and constraints in manifolds, JuliaManifolds completely removes this problem, because we try to minimize the amount of computation that is done with parametrizations. We have a generic interface that doesn't require introducing such parametrization. Next point is that manifold-based algorithms allow for respecting the geometry of your data. For example, if you have data on a sphere, then it's not a flat space. It has certain curvature, and handling this curvature in, for example, a statistical model may result in having a model that is more appropriate for your data. Okay, and last point, sometimes you may already use manifolds for something. For example, they are fairly popular in physics, but also in robotics, for example. They are also quite heavily used, especially Lie groups, which Ron will be talking about in a moment. Okay, so let's talk about what a manifold actually is. A manifold is basically any set. We don't have many restrictions on what this set is. We need to specify a certain number that is the dimension of the manifold, and it basically tells how many continuous parameters this set has. So, for example, if you have standard d-dimensional Euclidean space, then this is the dimension of this Euclidean manifold. For example, a plane has 2 dimensions, a straight line has 1 dimension. So that's fairly intuitive. A standard sphere has 2 dimensions, because we need to specify 2 coordinates to identify a point on a sphere. The next part that is required is a collection of charts. So this is basically what I was talking about, the way of removing constraint by introducing a chart and mapping everything into Euclidean space. This is the condition that says that we can do this with a manifold around any point we want. The trick is that here we only require these charts to be defined in a certain neighborhood of each point. It's not a global thing, it's completely local, and we may need multiple charts to cover the entire manifold. And thus we cannot rely on just having one chart. This is why we have the I index here. And those charts provide a local view of the manifold as a standard Euclidean space. So this may be also viewed as a certain kind of local flattening of the manifold. There are also some topological conditions that tell in what kinds of sets and what kind of structures are disallowed, basically. It's probably the part that is the most challenging from a theoretical point of view when you study manifolds. But it's, I think, not particularly required to know to use JuliaManifolds. You may know nothing about topology, and it's okay. I think it's fair to say that topology basically is for restricting certain pathological cases that may appear when you consider the other points, and we just say that some things are not well behaved, and we don't consider them as manifolds. And last part is intrinsic operations. If we only have charts, then we can't do much with manifolds. Intrinsic operations are certain operations on manifold that don't depend on the selection of a chart. Basically, that's how we can think about them. And why do we care? Well, we care because charts introduce those not very nice things that they are not global but only local. We want operations to be generally chart free. This way we don't have to flatten, um, we don't have to switch charts. It's basically much simpler. And I will talk in a moment what operations are available that are intrinsic. And this is a fairly large set of operations. Lots of algorithms can be expressed in such an intrinsic way. So it's, I think, quite a good justification to work on manifolds. Here is an example of what are the problems with charts. On the left-hand side, we have a simple manifold, a circle. It's a manifold. We have two charts, phi1 and phi2, and they map the parts of the circle to a 0, 1 interval. You can, of course, perform an operations on this interval, but you may notice that those intervals don't cover the entire circle. They have small gaps that are necessary to perform this unwrapping. So that's why it's local. Generally, mathematicians tend to point out that there may be lots of charts needed for standard manifolds that we commonly encounter. We basically need at most 2 charts for corrected components. So it's not that many that we have to introduce, but we very often need more than one, and then we need to figure out how to switch between them. And switching is done usually by transition map. So this is how we can switch between one set of parameterizations and another one. And now, what isn't a manifold? Basically, most things kind of are manifolds. So basically, any complicated structure can either be considered a manifold or decomposed into ones with some minor restrictions. This may be somewhat interesting. For example, a closed interval is not a manifold because it's not at the endpoints locally like a Euclidean space. It is similar to a closed mm, in a closed interval. So it is introduced as set of non-negative real numbers a little bit below. And this is why it's not a manifold. In a square also it's not a manifold. It's a so-called manifold with corners, but those are basically technical issues here. It's not like we cannot work with them with JuliaManifolds. That they just present certain challenges that mathematicians tried to sweep under the rug and don't handle. But it's perfectly possible using some additional considerations. One additional non-example of a manifold is a plane with a duplicating pointing. It's a standard example in topology of why the the topological conditions are necessary to avoid pathological cases. Basically, if we have 2 points on a manifold, we would like to always be able to separate them using open neighborhoods that are disjoint. If we have a duplicated point on a plane, then this separation is not possible. This causes issues. So that's something we disallow. There are also other counterexamples in topology, but they are often very weird, so I will not be talking about them. There are also some generalizations of the concept of manifold that we, to a certain degree, consider. So, for example, we have manifolds with boundary or manifolds with corners that don't locally look like Euclidean space, but like a Euclidean space times this set of non-negative real numbers, and this way we can handle certain constraints on such sets. Another important concept here are stratified spaces. We currently don't do much with them, but it's on our roadmap to include them in what we support. And they significantly expand the number of things we can do. So let's now talk what are the basic operations that we can have on a manifold. Basic concepts. One of central concepts is the concept of tangent vectors. Tangent vectors basically extend two standard concepts in Euclidean from the Euclidean setting: a velocity of a curve. So if we have a curve, we can compute its the derivative and see how fast it's going and in which direction. And another concept that is also expressed by the tangent vectors are directional derivatives. So we may have a function, a scalar function of on some space, and we may have a direction which points in which we want to calculate directional derivative, and you can also do this using tangent vectors. Okay, this definition is quite technical, but what's important is that basically tangent vectors are those arrows. You can think of them as arrows that point into the direction a curve is going. The definition is quite technical because there are multiple curves that may pass through a point in the same direction. So we have to consider that such a tangent vector may be represented using different curves. But that's not how we usually represent tangent vectors. We usually do it using either numbers in an embedding. That's one most common way, and another way is expressing using coordinates in a certain basis. Sometimes it may come from, for example, some chart, and in a chart it's the most easy to see how it works. Okay, there are many more operations that are that we can introduce on a manifold. I have grouped them here in a certain in a few certain categories. The basic structure that we have just talked about is the topological structure, but we also can have, for example, a way to calculate volumes on a manifold. It's one additional structure. It's a key part if you want to introduce densities on the manifolds, for example, for statistics. We have an affine connection, which is another important part if we want to relate tangent vectors at different points to each other. We have the triangulations, but this is not something that we work much on JuliaManifolds. It's something I'm thinking about doing at some point, but not right now. We have group operations which lead to regroups. In the next talk, we have a symplectic form, which is sort of important in some physical applications because it can connect Hamiltonian of a system with the tangent vector along which an object is evolving. We have finally the inner product, which is the central point of the Riemannian geometry. And I have also written distance there. It's not particularly well known thing, but you can generalize Riemannian manifolds to allow for more complicated ways of calculating distances between points, and so it also mostly works. The arrows basically are there to point out which concepts are more specific. So, for example, if we have a group operation, then it implies that there should be a certain compatible affine connection and a density on a manifold. If we have an inner product, it implies a certain standard symplectic form, certain way of calculating distances, and an affine connection as well to connect different tangent spaces. Affine connection is basically the central thing that we need to be able to do much with a manifold. I think it's not very well introduced in most books, at least if you want to do some computations. It's actually a fairly simple concept if you know ordinary differential equations, because it's basically just a system of ordinary differential equations on a manifold, which allows you to transport tangent vectors at one point to tangent vectors on another point. This, for example, is useful if you want to calculate geodesics. So you start in one point on a manifold, you have a tangent vector, so you know that you want to go in roughly this direction. And without an affine connection, you wouldn't know how to go further. If you want to, if you pre-picked one curve, then if you would go one direction, another curve, another direction, it doesn't specify which the direction should be chosen. This is done by an affine connection. This leads to the concept of exponential map, which is basically how we move from one point in another direction. We have a logarithmic map, which does the opposite. We have a distance concept on manifolds, where we can calculate distance between two different points. If they are connected by a geodesic, we have an inner product on manifolds that basically enables us to generalize most standard algorithms to manifolds. But the key part here is that we do not need charts to do most of these computations. JuliaManifolds basically collects all algorithms, all the different algorithms that can work in this way. We have a fairly large ecosystem. We support lots of the different manifolds. We have, for example, mono.jl, which I think is interesting. It is a package for nonlinear optimization. We have support for link groups, which is very important for robotics. We have a lightweight interface package. If you want to do something on manifolds, you may just depend on a fairly lightweight package to do this. We have support for differential equations on manifolds. This is one part where I think SciML is not really not having all state-of-the-art solvers. For example, Lie group solvers in SciML are fairly limited in what they can do. Here they are fully generic. You can do them for whatever they are capable, and they basically generalize standard Euclidean solvers for certain ODEs. And I think the one important part for this is that you can solve certain algebraic differential equations without having to worry about constraints. You just turn constraints into geometry using this approach. And there are also a few work in progress things. Here is overview how to do all those things in Manifolds.jl. I will share those slides later. I think we don't have enough time to go over this, but one important thing here about our interface design is that all operations that we implement have manifold as the first object in a call. So that way you know what we are working with, and all other the points and tangent vectors are type unconstrained. We can represent those concepts using any type we need. They can be static arrays, standard arrays, array partitions, whatever. And here is a small example of how we can generalize a standard Euclidean algorithm to manifolds. You can, for example, have Hermite interpolation that looks very similar to what is done on Euclidean manifolds, but using JuliaManifolds, you can easily generalize to anything. For example, you have logarithmic and exponential map here, which are usually fairly easy to find out for your manifold, but there is also differential of the log for with respect to argument, and this is something that is usually more complicated to find out. We have that for many manifolds. Okay. None of them will be in the poster session, so maybe we'll leave it to there. Also, a few words about statistics on manifolds. This is also something that has seen a lot of the development. There are a few different external packages that developed those concepts. We have, for example, one package by Julia Robotics that uses it for inference in their solvers. And we also have a very new package that does Kalman filters on manifolds in a very generic way. And it basically shows that you can work with Kalman filters on very generic spaces. In the future, we'll surely add more manifolds. We have some ideas to add branch and bound things to our library. We will improve support for manifolds with corners, so that basically anything that is continuous like would work here. There are some performance improvements to be made also. Our approach is basically make as much as possible work correctly and optimize what is necessary to be fast. So there are some things that could be faster. We have lots of ideas to develop, so I think it's a very active set of packages that is being developed here, and we have also a paper that may read if you are interested. Okay, I think that we are out of time right now, so I'll stop here.
We've got time for one question. I'll line you set up. Those are two questions. And thank you, Mateusz, for that comment. Thank you.
So not exactly a programming question, but since this is actually relevant to like my research, When we talk about tangent spaces as like being velocity of curves versus like the differential operators in some directions, you've mentioned how they're basically the same notion in finite dimensions, but not in infinite dimensions. Is there like a way of describing that difference, or is that a bit too complicated to answer?
Uh, Okay, so the difference between finite infinite dimensions in this case, it's fairly complicated. I think it's mostly technical and not something we need to worry about. I just also have done some work with infinite dimensional manifolds, and there is also some complications that we do that you may have. Directional derivatives that are very weird in a way that they don't point in any direction. But it's very theoretical. This is another example of mathematicians considering very exotic things, and they don't really have much practical application. But I think it's quite interesting that such things appear in theory.
And also in practice, at some point, you have to discretize. So, I mean, to get it to numbers, something infinite dimension, you have to approximate by a finite amount of points or something. And definitely something that we want to cover, but maybe also someone that has to come along and say, I need this, can you help me? So that's sometimes also just driven by that.
Awesome. Thank you.
I mean, yes. Thank you, Matthias. It's Rachel.